We will start this afternoon session. It is my pleasure to introduce our third speaker, Anthony Nouy. First of all, thank you very much for having accepted the invitation to speak at AMReX. So Anthony did his PhD thesis at École Normale de Cachan, where he has been also a lecturer. Then he joined Université de Nantes as an associate professor, and since 2010 he is a full professor at École Centrale Nantes. His research deals with several aspects of approximation theory and scientific computing, and in particular he is a specialist in tensor methods, and this will also be the object of his lectures today. So thank you very much, and the floor is yours.
Thank you, Domino. Thanks a lot for the invitation to give this course. So in this course, I want to introduce you approximation tools called tensor networks. So I will take some time to introduce these objects, and then we will talk about some approximation and learning problems using these tools. So first, tensor networks. Maybe you have heard this name. It comes from different disciplines where you have problems involving multivariate functions or multidimensional arrays. So it has a long history in quantum physics. These objects appeared first in this discipline, involving very high-dimensional problems for the representation of complex systems. It appeared independently in numerical analysis. In fact, a particular class of tensor networks called tree tensor networks, and as an extension of low-rank decompositions of higher-order tensors. And recently, it has been used a lot, and there are many developments in other fields, in statistics, data science, and probabilistic modeling. Okay, so first I would like to motivate the use of tensor networks in different contexts, and these different contexts in fact depend essentially on the available information you have on your functions or tensors. So the first problem involving tensors is the approximation of a known tensor U with respect to a certain norm. And here you aim at finding a tensor network with a low complexity that minimizes some distance to the solution U. So here the aim is the compression of information, compressing your tensor U with an object having lower complexity, or the extraction of information from U. This is related to the field of data analysis. Second kind of problem is when you try to solve an equation, an operator equation, AU equal B. For example, high-dimensional PDEs arising in quantum physics or uncertainty quantification with parameter-dependent PDEs we have seen in the course of Albert, or many problems in stochastic calculus. Here the aim is to find a tensor network with a low complexity that approximate well the solution. So you can do it in practice by minimizing some residual norm over tensor networks. I will come to this later in the course. So here the aim is to obtain an approximation of the solution with a low computational complexity when you use tensor networks. Okay. Another setting involving a lot of research in tensor networks is tensor completion problems, where you have a multidimensional array, and what you know are some entries of this array. So you have partial information on your multidimensional array, and you want to recover the initial tensor. So this is an ill-posed problem, of course. So here using tensor networks may make the problem well posed. So you would like to exploit some structure of your multidimensional array in order to be able to recover it from partial information. A related problem, a more challenging problem, are inverse problems, where you want to identify a tensor from indirect and partial observations. So we have seen this type of problem in the course of Albert. So you are given some observation Y that are some transformation of U through an observation map, possibly noisy. And here using tensor networks is a way to make the problem well posed. So in practice, you will try to minimize some distance from the observation and the prediction given by your tensor network through the observation map. Okay, another topic that I will address more at the end of this course today is the approximation of a function u from evaluation of this function. So this is clearly a follow-up of the course of Albert. If you do it in a least square setting, you will in practice minimize the squared L2 norm between the evaluation of your function and the prediction given by your approximation V. So here the use of tensor networks is a way to exploit, I would say if you are given the samples, so this is a passive acquisition setting that Albert mentioned, you will exploit this structure of your function and use tensor networks to exploit at best the available information of your function. If you are in an active acquisition setting or active learning setting, you will use tensor network to obtain a good approximation using a small number of evaluations. So finally, very rapidly on this last field that in fact motivated many works in recent days, are a problem in learning, either supervised learning or unsupervised learning, where tensor networks are used for exploiting structures of high-dimensional functions, and they have appeared as a very powerful class of functions for addressing many tasks, regression, classification, estimation of high-dimensional density. Okay, I will not spend too much time on this classical statistical learning setting in this course, but I will give you at the end some references, some entries to this field also. Okay, so the outline of the course, the course is split in 3 parts. First, I will talk about tensors, tell you what are these objects. I will tell you about notion of ranks of tensors, and then introduce some related tensor formats exploiting low-rank structures. And we will see these formats as particular cases of a more general tensor network. In the second part, I would like to give you some results obtained from the approximation theoretical side on tensor networks, what we can expect from them to approximate some classical or less classical function classes. I will tell you about what are the results that we have, what are the open questions in the field. And part 3 is kind of miscellaneous. I will maybe not cover all of the part 3, but part 3 contains many algorithmic aspects when you try to compute with tensor networks in the different settings I have mentioned, when you have partial information of the function, an equation satisfied by your function, and so on and so on. Okay, that's the program for today. Okay, so first let me introduce what is a tensor. So first you will have a very intuitive introduction of tensors here. If you are given d index sets, I nu are integers from 1 to n nu, I introduce a multi-index set I, which is a product of I1, I2 until ID. And an element V of the vector space Ri is called a tensor of order D. This tensor will have a representation as a multidimensional array with entries Vi, okay, indexed by I1, I2, and so on, that contains the coefficients of V in a particular basis of Ri. Okay, think about a matrix as a representation of a linear map in a particular basis. Okay. So a tensor is an element of a vector space, and the multidimensional array, which is here, is a representation of this object in a particular basis. So in the following, for entries of a tensor, I will sometimes use indices like this, or see the object as a function that takes as an entry the index. Okay, this is completely equivalent point of view. The order D is also sometimes called the dimension, depending on the field, dimension of the tensor. And we call also the different dimensions the ways or the modes in other disciplines. Okay, so I will essentially call this the order of a tensor, but it has other names in other disciplines. So here you have an illustration of a one-dimensional array, which is a representation of a vector. Here, representation of a matrix, and a representation of a three-dimensional array. Okay, so I introduce here a quite useful representation of tensors, and Mazen tomorrow in the end session will give you more about this practical representation of tensors. This is a graphical representation of tensors that we call tensor diagram notation, where a tensor is represented by a solid shape that you see here, and tensor indices are notated by lines emanating from this shape. Okay, so here you have a tensor of order 1 with only one line emanating from the tensor with index I1. Here you have the representation of a matrix with two indices, and here a third order tensor. Okay, then some operation between tensors will be easily represented using this tensor diagram notation. When you connect two lines emanating from two tensors, here I have a tensor V, a tensor A. The tensor A has two lines emanating from it, so it's a matrix. The V here is a vector. I connect the two lines, so here I have an H, and it means a contraction over the corresponding indices of A and V. Okay, so this is no more than the matrix vector multiplication represented here in tensor diagram notation. Well, so now, given D vectors in these vector spaces, I define here what we call the elementary tensor product of these vectors. This is called an elementary tensor, and it is such that the entry I, for I equal I1 until ID, is the product of the entries of the individual vectors that you have here. Okay, so the representation here using matrix notation is simply the product of a vector V by the transpose of another. Okay, so this tensor product, elementary tensor product between two vectors, is represented like this when you identify your order 2 tensor with a matrix. And here you have a schematic representation of elementary tensor product of three vectors. Okay, so now we will denote a tensor space Ri, so the set of all tensors I have presented previously. We also denote it like this, so it's a tensor product of vector spaces, and it is defined as the linear span of elementary tensor product. All possible linear combination of these elementary objects that I have defined before. Okay, now let's talk about norms on these vector spaces. So we can define on this vector space what we call a canonical norm, also known as the Frobenius norm of matrices, but it's also called Frobenius norm for higher order tensors, which is defined as the square root of the sum of the squares of the entries. And this norm makes the space a Hilbert space. So this space coincides with the natural norms on L2 sequences defined on the index set I. This norm defined here, that we call the canonical norm, is the only norm associated with an inner product having this property here, that the norm of an elementary tensor product is the product of the norm of the individual vectors V1, V2, and so on. Okay, so I will come back on this property later. In tensor diagram notation, the operation we perform to compute the norm, so the square of the norm, which is the sum of the square of the entries. So this is a multiple sum over the multiple indices of your tensor that you can represent like this. You have the tensor V here, the tensor V here, with lines emanating from these tensors that represent the indices of the tensors, and you connect all these lines. That means you are summating over I1, I2, I3, and so on, the entries of V and V, okay? So if you want the inner product of a tensor V and a tensor W, you will have the V here, the W here, and the same tensor diagram notation for this inner product operation. Oh, sorry. Okay, now, so I was essentially talking here on tensors defined on a finite index set. now we can have exactly the same introduction of tensor product of functions. So now I consider a space V nu, which is a space of functions defined on some set X nu. Okay, nu represents a particular dimension, particular mode of my tensor. So this is a space of function defined on X nu. X nu, what it usually, in most of the result, I will show you, this will be R, or a subset of R, an interval, but it can be also C, N, Z, but it can be also more complicated sets, sets of vectors, sets of sequences, graphs, images, and today you can find applications of tensors in many applications involving functions defined on very complicated objects. Okay? Whatever the setting here, the tensor product of functions, V nu, will be denoted like this, and it's exactly the same as before. It's defined as the product of univariate functions evaluated, V1 evaluated at x1 times V2 evaluated at x2, and so on. Okay? So same presentation as before. Before we had that the x1, x2, and so on were just an integer between 1 and n nu. Now it can be x1 can be a more complicated object. So the definition of elementary tensor product is the same. So here you have a very, very simple example, a monomial, x to the power I with a tuple of integers is defined like this, and is an example of an elementary tensor, okay? Since it's a product of univariate functions. Well, now, in this more general setting, I can define again the algebraic tensor product of the spaces V nu as the linear span of elementary tensors. All possible linear combination of these objects that are products of univariate functions. Okay? So this is the space of all functions that you can write under this form with an arbitrary integer n, but the sum is finite. Okay? It's a finite sum of elementary tensors. This is called the algebraic tensor product of the spaces V1, V2 until Vd. A polynomial, sum of ai xi, is a particular example of an element of the tensor product of polynomial spaces. Okay? I will not go into more general settings, but if you are interested, you will find references at the end of this part where you can introduce tensor spaces with a very formal definition of tensor product that allow you to go beyond product of function spaces, okay? More general vector spaces. And this includes spaces of matrices or operators, but much more complicated vector spaces also. Well, now, this was a setting where I did not mention what was the dimension of my objects. But if you have infinite dimensional spaces V nu, okay, think about V nu being L2 space, for example. V nu could be a Hilbert space or Banach space. And if these V nu are infinite dimensional, this is an infinite dimensional space, but in general, it will not be complete, okay? If you have spaces V1, V2, and so on that are Hilbert spaces, infinite dimensional Hilbert spaces, this space will be an infinite dimensional space, not necessarily complete. So what you, in order to have a Hilbert or a Banach tensor space, you will have to complete the space, okay? So you can define like this a Hilbert or Banach tensor space by completing the algebraic tensor space with respect to the norm, with respect to a particular norm, okay? If this norm is associated with an inner product, it will result a Hilbert tensor space. If it is not associated with an inner product, it will result in a Banach space. if the spaces V nu are Hilbert spaces with inner products denoted like this and associated norms denoted like this, you can define a canonical inner product on V, which is defined for elementary tensors as follows. If you take the inner product of these two elementary tensors, it will be the product of the inner products of the different vectors you see here. Okay? Here I have defined the canonical inner product for elementary tensors, but you can extend this definition to the whole algebraic tensor space by linearity, bilinearity of your inner product, and then extend this notion by over the completed space. Okay? So this is a construction of tensor Hilbert spaces, tensor Banach spaces. Oh, wait. Okay. Ici. Alors, pour le moins. Ah oui. Ok, merci. Ok, parfait. Okay. So some examples, very briefly. LP spaces. You can take LP spaces of univariate functions, LP over an interval x1, x2, and so on. Take the algebraic tensor product of these spaces, but this space is not complete. If you complete it with respect to the LP norm, you obtain the space LP over the product set x1, x2, and so on. Okay? This holds for P between 1 and infinity, infinity excluded. Another example that we come later in some other examples are Buchner spaces, where I consider function defined on a measured set X with value in some Hilbert or Banach space W. Okay, so this Buchner space LPX W is the space of Buchner measurable function defined on X with value in W. And in fact, this has a structure of a tensor Banach space. It is the completion with respect to this Buchner norm here that we have seen already in some courses before, of the algebraic tensor space, tensor product space of W by L, scalar function valued, scalar valued function over X in LP. Okay, last example. Will not spend too much time on this, but you have here an example of Sobolev spaces. So the classical Sobolev space of function whose norm is can be defined the square of the norm as the sum of the square of the norm of the derivatives being taken such that the tuple alpha, the sum of the entries of the tuple is bounded by k. Okay, this is a classical norm on the Sobolev space HK, which is the completion with respect to this norm of the algebraic tensor product space of the HK space. But now, if I complete with respect to another norm, which is this one, where the square norm is defined as the sum of all derivatives with the tuple with maximal entries bounded by k, what we obtain when we complete, we obtain what is called the Sobolev space with mixed regularity, HK mech, which is a particular example of space associated with a canonical inner product, okay? The one that I mentioned before. This one has the norm, which is here, not the property of being a cross norm, and so the inner product associated with this norm, it's not a canonical norm. It's not a canonical inner product. Okay, so this was, yeah? Yes, indeed. Yeah, in fact, you have a result where, in fact, the completion you obtain here is the same as the completion of the completed spaces that you have here. So if you take something that is dense in the HK, which is here, it will result in the same space. Yeah. Yes. Yeah. Yeah. Okay. So now let's talk about representation of these objects. If you have a space V nu which has a certain basis, denoted phi I nu, then you will obtain a basis for your algebraic tensor space given by the tensor product of the basis of the individual spaces. Okay, called the product basis, tensor product basis. And the tensor V in the algebraic tensor space will admit a decomposition as a sum of coefficients AI times phi I, where the AI is a multidimensional array. Okay, so this is the counterpart of my first slide where I considered the vector space Ri, and I said that the multidimensional array is a representation of this tensor in a particular basis. So here it's the same, but it can be a much more general setting where when you have spaces here that admit some basis. Okay, so tensor V will be identified once the basis is chosen with the set of its coefficients, which is now again in the space Ri that I introduced before. Okay, so if you are in a Hilbert setting, and if the basis here that you have are orthonormal basis of this Hilbert spaces V nu, then the tensor product basis phi I will be an orthonormal basis in your Hilbert tensor space, which is equipped with a canonical norm. And a tensor that admits this decomposition on the orthonormal basis is such that the square of the Hilbert norm will be the sum of the square of the entries, which is the Frobenius norm of the tensor A of coefficients. Okay? So the map which associates to a tensor of coefficient A, the tensor which is sum of AI phi I, defines a linear isometry between L2I to V for finite dimensional spaces, and between L2I and the completion of V for infinite dimensional spaces. So of course, in practice, when we manipulate tensors, we'll usually in practice introduce bases and work with these objects that are coefficients of the representation of our tensor in a particular basis. Okay, I will come to this later on more concrete problems. Maybe for those who are familiar with the terminology used in learning, you can introduce associated with this basis of function of the variable x nu, what we call a feature map, phi nu, which takes the entry x nu and give you a vector, which is the evaluation of the basis function at the entry x nu. Okay? So this map is called the feature map associated with the space V nu. And you can introduce a tensor product feature map, which is a function defined on your product set X with value in the tensor space Ri, such that this feature map for a particular entry X is the elementary tensor product of the feature map of the spaces V1, V2, and so on, evaluated at X1, X2. And then I can have a nice representation of a tensor, Vx, as the canonical inner product between the coefficients A and the tensor product feature map phi x. Okay? This is a pointwise evaluation of your function V, which is given by an inner product between two tensors. And the tensor diagram notation for this is the following one. You have here a tensor A of order D, general tensor of coefficients, with indices I1, I2, and so on. And you have these components of the feature map, Phi1, Phi2, that have one line emanating from it, which is a particular variable x1, and the other is associated with the dimension of the output space of your feature map. Okay? And these lines here, these edges, represent contractions which is no more than the representation of the inner product you see here. Okay? Well, so this was the definition of tensors. So now, before introducing these objects called tensor networks, I will talk about tensor ranks. What is the definition of a tensor rank? So I start with something that you know. The rank of an order 2 tensor, U, in a tensor product of two spaces V and W. So the rank will be denoted rank of U. It is a minimal integer R such that U can be written as a sum of R term being elementary tensor product. Okay? The minimal integer R such that you have a representation under this form. If you identify your tensor U with a matrix with n rows and m columns, the rank defined here is no more than the matrix rank, okay? Which is the minimal integer such that you can write your matrix as a sum of outer product of two vectors Vk and Wk, represented here in matrix notation, VW transpose, where V is a matrix whose columns are the Vk, and W is a matrix whose columns are the Wk. Okay. A notion which will be important later also for tensor networks, the notion of singular value decomposition of tensors. So if you have two Hilbert spaces, V and W, possibly infinite dimensional, an algebraic tensor U in the algebraic tensor space V tensor product with W admits a singular value decomposition, which is a decomposition like this, with sigma k called the singular values that are positive numbers, and Vk and Wk are vectors in spaces V and W respectively. And the set of vectors Vk is orthonormal in V. Set of vectors Wk is orthonormal in W. Okay? This is a singular value decomposition. The rank of U for an algebraic tensor is finite, because U, we know that it is a finite linear combination of elementary tensor. So you can prove quite easily that the rank of an algebraic tensor is finite, and it coincides with a number of non-zero singular values. Okay? So computing a singular value decomposition is a way to obtain the rank of an algebraic tensor. So for matrices, probably you know this type of decomposition under another form. If U is identified with a matrix in R NM, you have this type of decomposition. If you store the vector Vk in a matrix V, the W in a matrix W, and the sigma k in the diagonal of a matrix S, you have this representation of the SVD, VSW transpose, with orthogonal matrices V and W and a diagonal matrix S. Okay, now short comment on singular value decomposition can be extended in the infinite dimensional setting for Hilbert tensor spaces. If you consider the completion of a tensor product of two spaces V and W with respect to a particular norm called the injective norm, in fact, if you see your tensor as a map from a Hilbert space V to W, this injective norm is related to the spectral norm or operator norm. Okay, so this is another term that you find in the literature on tensors, injective norm. Then the completions that you have here coincide with the space of compact operators when you identify a tensor with an operator. And these compact operators admit also a singular value decomposition. So in this infinite dimensional setting, you will have a decomposition also under this form, but now maybe you have possibly infinitely many singular values that are non-zero. Okay? Well, so two examples in the literature when you have this singular value decomposition of infinite dimensional tensors are settings where you consider functions defined over a space-time domain. consider a Hilbert space of function defined on the domain omega, and a function defined on the time interval with value in V. I assume that U is in the Buchner space L2IV. Okay. If you remember, I told you that this Buchner space is a Hilbert tensor space. Okay. And you will have a singular value decomposition written like this, with here time functions, here functions in the space V of functions defined on omega. And this is called the proper orthogonal decomposition. Okay. Well, this is usually called like this when you consider a space-time function. If you are in a probabilistic setting where you have a function U defined on a probability space omega with value in some Hilbert space V, and you assume this L2, you make this L2 assumption, you are again in this Buchner setting, and you have a singular value decomposition called the Karenen-Love decomposition. Okay, where here the variables are now here WK are now random variables defined on the probability space omega, and the VK are elements of the space V. Okay, so now we'll talk about low-rank tensors, approximating with low-rank tensors, and so on. So what we will do is define sets of tensors that have a low rank. So I introduce this set here, R indexed by R, which is a set of all order 2 tensors with a rank bounded by R. So clearly this space is not a linear space. Okay? And nor a convex set. If you take a convex combination of 2 elements in this set, typically you will have a rank which is 2R. Okay? So this is not linear, this is not convex set, but yet it has many favorable properties for a numerical use. First, you have that the map which associates to V its rank is lower semi-continuous. And the implication of this is that the set here is a closed set. Then you will have interesting properties of optimization problem having solutions. For example, if you optimize a convex functional over this set, there will exist solution, maybe not unique because you don't have strict convexity of this set, but okay, you will have well-posed net of optimization problem. Something interesting, I will not talk a lot on this in this talk, is the fact that this set is clearly a union of set of tensors with a fixed rank, going from 1 to R, and all these sets are smooth manifolds. Okay, so you can exploit this nice geometrical property in the practice for devising optimization method exploiting the geometry of these sets. Introduce dynamical low-rank approximation for evolution problems. Fabio worked a lot on this dynamical low-rank approximation. So I will not talk a lot about this, but there have been a lot of work exploiting this manifold structure of these sets. Okay, now let's go to higher order tensor. I can define in the same way a notion of rank called canonical rank of a tensor as the minimal integer R such that the tensor can be written as a sum of R elementary tensors. Okay? So here I give again some examples. A monomial is a tensor with a rank 1. If I take a polynomial, as in the presentation of Albert, which is the sum of indices I over an index set lambda of AI xi, where xi are the monomials, this will have a canonical rank equal to the cardinal of the set lambda. If I take a Gaussian function, exponential of minus alpha, the squared norm of x minus some vector a, this can be written as a product of exponentials of individual variables x1, x2, and so on, and clearly it has a rank 1. The function which is here 1 over the 2 norm of x, this function now has an infinite rank. Okay? Infinite canonical rank. Okay, so now I can introduce a set of tensor V with a rank bounded by R. Okay, I fix an integer R and I consider this set of tensors. So this is the set of all functions that can be represented into this form with R term at maximum. The storage complexity of tensors in this set is essentially R times the storage complexity of an elementary tensor here. And what is the complexity of storing this? It's the sum of the complexity of storing each of these guys, and it will depend on the dimension of the individual spaces, V1, V2, and so on. So you have R times the sum of the dimension of the spaces. So essentially, it will be linear in the dimension. And this is why this kind of format for approximation purposes have attracted a lot of attention, because it allows to manipulate an object in high dimension with a storage complexity which does not present the curse of dimensionality. Okay? It's just linear in the number of dimensions. Later, in the second part, I will tell you about what we can expect from this. This is another thing. If you are a particular function you try to approximate, you cannot just say, because I use this, I break the curse of dimensionality, because you have to say what is the range that you need for having a good approximation, or what you want with your particular problem. Okay, and we will see that this format sometimes in standard problem will suffer from the curse of dimensionality, as other approximation tools suffer. Okay. Okay, so now, what are the properties of this set? For d greater than 3, the set here of tensors with canonical rank bounded by R loses many of the favorable properties that I have mentioned for matrix case, or the two case. So first, before I told you, you can compute a SVD, look at what are the non-zero singular values, and you will obtain the rank. Okay. Now, we know that determining the rank, the canonical rank of a tensor of order d greater than 3 is an NP-hard problem. Okay, there is no efficient algorithm for computing the rank of a tensor. Also, from the geometrical point of view, you don't have the nice property of before. So we know that this set is not an algebraic variety. You have no notion of singular value decomposition related to this notion of rank. Maybe more dramatic from the numerical point of view is that the map which is here, which associates to V its rank, is not low or semi-continuous. So the set which is here is not closed. So you will in general have optimization problem over these sets that are ill-posed problem, and you will see it in computation with instability in your algorithm typically. So you can do things to avoid these problems by introducing regularization, but essentially it's equivalent to putting some constraints and considering another set than this set. Okay, directly using this set for a numerical purpose is usually not stable. About this non-closedness property, here I give you a simple example that allows to see the problem. Consider the order 3 tensor whose rank is 3. So it's quite easy to see that the way it is defined, the rank is 3. It's a sum of 3 elementary tensors with either a vector A or B as a different components. So this has a canonical rank equal to 3. And here I defined a sequence of tensors that are differences between 2 elementary tensors. So this is a tensor with canonical rank equal to 2. So you see here the definition. The first component here is n times a plus 1 over nb. The same here, the same here. And here is elementary tensors a times a. Okay, but by multilinearity, you can expand this and very easily see that when n goes to infinity, you will converge to V. So we have found here a set, a sequence of order 2 tensors with canonical rank, of order 3 tensors with canonical rank 2 that converge to a tensor of rank 3. Okay, that shows that the set of tensors with canonical rank bounded by 2 is not closed. Okay. Okay, this is the comment I gave. Yeah.
My question, because I saw this example a couple of times. So, if you impose that the factors are uniformly bounded, here n is
yeah, it becomes closed.
Right.
Yeah.
So there is a theorem there that says it's closed.
Yeah. Yes. This is why I said if you have an optimization problem of these sets and you introduce some Tikhonov regularization, for example, it's equivalent to bounding these coefficients, and you again obtain a well-posed nest of your problem because the set of tensors like this with bounded elements is closed.
Is it easy to prove this?
Yes.
Okay.
Yeah. Okay. So now we have seen that this notion of rank is not very suitable for numerical purpose in a high dimension, for higher order tensors. So now I will introduce another notion of rank, which is quite natural, which is associated with a particular group of dimensions. I introduce alpha, a subset of the set of dimension 1 to D. Then a tensor U in this algebraic tensor space can be identified with an order 2 tensors by grouping on one side the indices alpha and on the other side the alpha complementary. Okay? So here I introduce this notation M alpha, which is called the matricization operator. It takes a tensor U in the tensor space V and gives you something in a tensor space V alpha, tensor product with V alpha complementary. Okay? So this is seen as an order 2 tensor. You can I can illustrate this here. I have a 3 order tensor here represented by this hypercube or hyperrectangle, and the matricization associated with the first dimension 1, okay, will give you a matrix whose columns are what is called the different fibers, all the columns that you can see here in the two slices. Okay? If I matricize along the second dimension, I will obtain a matrix with 4 lines and as many columns as the product of dimension 1 and 3. Okay? What we call the alpha rank of a tensor U is nothing but the classical rank of the order 2 tensors that you see here. Okay, so I will denote it rank alpha. Rank alpha of a tensor U is the rank, as defined before for order 2 tensors, of the matricization of U, the alpha matricization of U. So of course you have as many notions of ranks for a tensor as the way of partitioning your set of dimensions. Okay, there will be the notion of rank for each subset of variable alpha. With this, you can clearly see that the rank alpha is equal to the rank alpha complementary. Okay. Well, so here about functions, it's the same for functions. If you have a multivariate function with a rank alpha U bounded by R alpha, it means that it can be decomposed as a sum of functions of 2 groups of variables. The variable x alpha is the collection of variable xi for I in the set alpha. Okay? Well, so some examples of alpha rank. We played the game with canonical rank, so now let's consider a few functions. So the first function here is a product of univariate functions. So clearly it has a canonical rank equal to 1, but it has also all alpha ranks equal to 1. You can see it clearly because this function can be written as a product of two functions of groups of variables. Okay, u alpha x alpha is nothing but the product of ui xi for I in alpha. So therefore, the alpha rank of u is also equal to 1 for any group of variable alpha. If I take this function with a canonical rank bounded by R, it's a sum of R elementary tensors. Clearly, it can be written also as a sum of product of function of groups of variables, okay, by grouping the different functions here with the set alpha associated with the set alpha or alpha complementary. Then clearly, from this, you see that the rank alpha of u is bounded by R. Okay? The implication of this is that the alpha rank of a function u is bounded by the canonical rank. Okay? Is it clear? Okay, now another set of functions. Look at this function, u of x, which is a sum of univariate functions. This is a type of function appearing in many domains. This is called additive functions, used a lot in statistics, for example. And clearly, this can be written as a sum of two functions of group of variable. Okay, you group the different functions that are here in two sets. Okay, and written like this, it's clear that the alpha rank of u, because it is a sum of two functions of product function of group of variable, the rank is bounded by 2. Okay? Well, something more tricky, if you consider a function ux, which is a product over of functions of group of variable, where the alpha is in some collection of disjoint subsets, you can play with this notion of rank and obtain a bound of the ranks of your function. Okay, I don't go into the detail of this, but I let you this as an exercise. So you can play with this, and Mazen prepared you some examples where you will have to play with this notion of ranks, try to find ranks and encoding in the different formats I will present you some particular functions. Okay, a notion, I will try to go quickly on this, but there is a very nice notion of minimal subspaces associated with tensors that allows to understand the formats I will present later. So let me make it briefly. For a particular alpha, which is a subset of dimensions, you can define what we call the minimal subspace of function, minimal subspace associated with u and the collection of dimension alpha as the smallest subspace such that your matricization of u is in the product of u alpha and v alpha complementary. So if you think about functions, it's the smallest space of function of the group of variable x alpha that you need to represent your multivariate function. Okay, and the alpha rank is nothing but the dimension of this minimal subspace. Okay, and then you have several interesting properties of these minimal subspaces. First, if you are given a certain partition of your set of dimensions, so alpha is a group of dimensions, alpha 1, alpha 2, etc., all are groups of variables that form a partition of D. And you can prove that a tensor lives in the tensor product of its minimal subspaces. Okay, first property. Second property is that these minimal subspaces satisfy a hierarchy property. If you have a collection of variable alpha and you have a partition beta 1, beta 2, beta s of this alpha, it holds that the minimal subspace associated with alpha lives in the tensor product of the minimal subspaces associated with the element of the partition of alpha. Okay? And this implies an interesting property that you will need to analyze the property of the tensor formats that I will introduce, that the rank alpha of U is bounded by the product of the beta k rank of U for beta k forming a partition of alpha. And you have also an additional property that comes from these inclusions. Okay, you can also bound the rank of an element of the partition of alpha by a product of ranks like this. Okay, and then you have an example here. I will not go into detail of this, but you can look at this example where for a particular function given here, cos of x1 plus x2, x2 plus x1, x2 plus 2, x3, okay, we play with this, and I computed all minimal subspaces of this function. You can check this, the ranks associated, and by doing this work, you will see that you can check that the different properties I have mentioned before, the nestedness property is well satisfied. Okay, I let you look by yourself at this example. Okay, now we have all this notion in hand, and we will introduce a first family of tensor networks, in fact, that appeared in the literature with another name called hierarchical tensor formats or tree-based tensor formats. This has been introduced by Akbush and Kuhn in 2009, but you will see later that specific cases of this appeared much more earlier in the physics literature. But I will give you an introduction here based on the notion of alpha ranks, okay, which is not the traditional introduction of these formats in other literature. Okay, so what we call the tree-based tensor format is a subset of tensors whose alpha rank is bounded by some integer alpha, R alpha, sorry, for any alpha, for all alpha in a certain collection T, which is a dimension partition tree. What is the dimension partition tree of the set of dimensions? If you have a set of dimension 1 to 6, a dimension partition tree is a sequential partitioning of this set of dimensions. So here you see that at the first level, I partition the set of dimensions into two disjoint sets. And at the next level, I will again introduce a partition of this set, okay, with two disjoint sets here. And until singletons here that are called the leaves of the tree. Yeah? I can repeat your question? Yeah.
Excuse me, does this mean that each partition in this tree means the matricization of the tensor sequentially, or if I'm getting it wrong?
No, here it's just, okay, I introduce a tree, which is like this. And now I define a subset of tensors, okay, such that the rank 1 will be bounded by some integer, the rank 2 also, and so on, and also the rank 1, 2, 3, the rank 2, 3. So what I will impose as a structure for my tensor is just associated with these alpha sets, okay? Here, if I introduce this format, I cannot tell you what is the rank, let's say 2, 4, okay? 2, 4 is not a node of this tree. I do not impose anything on this. It can be very high, maybe. Even if I impose low rank for any of these groups, maybe the rank 2, 4 will be high. Okay, there is no constraint on other alpha ranks. I just impose these ranks. Okay. Yeah.
Isn't there a constraint as a result of the other ranks that you opposed if you transform?
Yeah, of course, the rank 4, 2, 4, for example, will be bounded by the product of the rank 2 and the rank 4. But I don't know exactly what it will be. I know, but indeed I know a bound. What is clear is that the alpha rank of a tensor, with the hierarchy I mentioned before, will be always bounded by the product of the ranks associated with the singletons in the set alpha. Okay, but if you have a huge set alpha, this is not very interesting, this bound in general. Okay, so you will have to work more in order to have sharper bounds. Okay, so in fact, so this definition here, okay, it's quite nice. I constrain the alpha ranks, but okay, what is the form of this tensor? Yeah.
So you mean that it's better if the tree that we have for the alpha rank, is it better that we have like more deep tree or more wide?
This is a question that I will address in the approximation part,
yeah.
Because we will have to ask what is the task I want to solve.
Yeah, for the alpha
and
rank.
Okay, I will in the part 2 I will have some comparison between different trees. Like for example, if you have something given with this tree, can you encode it with another tree, okay, in another format, and what can you say about the ranks in this different format? I will address this in part 2. Okay, so the question is now, what is a practical representation of such an object? Can I represent a tensor V, like in this set, with a practical representation? And the answer is yes, if you introduce for T a dimension partition tree. And I will show you how to come up with a practical representation of these tensors. Suppose you take a tensor V, in this tensor format, hierarchical tensor format, with a T rank, a tuple of rank or alpha. Okay. So at the first level, I said I partition the set of dimensions. So here it's a bipartite partition. What you know from the inclusion of minimal subspaces, remember, a tensor belongs to the tensor product of its minimal subspaces. These minimal subspaces have a dimension equal to the alpha rank imposed, okay? So since V is in the minimal subspace associated with 1, 2, 3, tensor product with minimal subspace associated with 4, 5, 6, I know that I can represent V as a sum, as a double sum, okay, over from 1 to R1 to 3 and 1 over R4, 5, 6 of product of function of the group of variable 1, 2, 3 and product of the function of variable 4, 5, 6. So another way to say it, if the minimal subspaces have dimension R beta, you introduce basis of these minimal subspaces and you know that Vx will have a representation in this tensor product basis. Okay? Is it clear? Yeah. These are bases of the minimal subspaces of the function. And this is the set of coefficients in this tensor product basis of minimal subspaces. In tensor diagram notation, this is the representation of this first step. You have here tensors with two indices. Here it's a group of variable 1, 2, 3. Here it's a summation index. The same here. So you can see these objects as feature maps associated with the minimal subspaces of your function. And here is a set of coefficients. And these two edges means the contractions you see here. Okay? So this was the first level. But then you have the other property that the minimal subspace associated with alpha equal 1, 2, 3 is included in the product of minimal subspaces associated with 1 and 2, 3. Which means that for alpha equal 1, 2, 3, you can expand it again in a product basis of the minimal subspaces associated with the sons or children of the node 1, 2, 3. Is it clear? Okay, so this element of the minimal these are elements of the basis of the minimal subspace alpha that I represent as a linear combination of products of the basis of the minimal subspaces associated with the partition of alpha. Okay? So this is the second step. Now I know that there exists a representation like this with here algebraic tensors of coefficients. And here, these are collections of functions depending on x1, x2, 3. And there is a last step because there is still one node here to split, for which we will introduce a partition. And we end up with a representation like this. In tensor diagram notation, you have a collection of tensors that are usually called the core tensors of the representation in hierarchical format. And here you have at the very end V1, V2, and so on that represent basis of the minimal subspaces associated with 1, 2, 3, and so on. For a representation that I can write like this, it's not very convenient notation, but okay, V can be represented as a multiple sum. All these sums correspond to the different contractions you see here over the edges of products of entries of the core tensors and entries of the different tensors you see here on the leaves. Okay? So maybe it's better to see it like this, the graphical representation, but this is the explicit representation. So we have now an explicit representation of an element of the tensor format, of the tree-based tensor format, with respect to parameters that are given by these core tensors and these functions. I can go a little bit further. If these functions admit a representation in a certain basis, okay, so if this is a basis for the space V alpha, or alpha, a leaf of my tree, I will obtain a representation Vx as a sum of entries of a tensor A times the tensor product basis here, with the tensor A, which can be represented in tensor diagram notation like this. The C1, C2, C3, and so on that you see here is the set of coefficients of the basis of the minimal subspaces associated with the leaves in the particular basis you have introduced. Okay? So, at the end, the practical representation of this object is not too complicated. You have a collection of tensors that are just multidimensional arrays that you have to store on your computer. And if you want to evaluate such a tensor, you will have to do some tensor algebra and do some contractions between tensors. Yeah?
Thank you. At this point, do we have an assumption on the K1, K2, K23 regarding the alpha rank? Or no?
For the moment, what I consider is a representation of an element in a set where I impose the rank. I impose a bound of the rank. Okay? So if you say all the R alpha are 2, you define a set that can be represented like this, where the summation indices here go just over until 2 for every edge. For the moment, you impose the rank. The question will be afterwards, what we can expect from this set where we bound the rank by 2. Will I obtain a good approximation or not? But you will see that we will play with these ranks after. We'll see when it's interesting to have an heterogeneous rank and so on. Okay.
So for now, the case are only
given. 2. Here it's given.
Okay.
So if you say, how can I represent the tensor V whose alpha ranks are all bounded by 4? You will have here a representation with multidimensional arrays here, with all dimensions bounded. Number of the size of this array will be bounded by 4 on each dimension.
Okay. Thank you.
Any other question? Yeah.
And this representation is an exact one. It's not an approximate one.
Yeah. Every tensor in the set I have defined has an exact representation like this. Okay. So here, this is where you see the terminology 3 tensor networks that appear in the literature in physics and which is quite common today. You have a network of tensors connected by edges that represent contractions between these tensors, okay? So you can see it as a tensor network, which is organized in a tree, okay? Well, now about the representation complexity. So it's related to your question. If you give me a certain rank, I know that I can store the object V with a complexity which is the sum of storing the complexity of storing each individual tensor in the network. And I know the different sizes of the tensors. That depends on the ranks for the core tensors and also on the dimension of the spaces V1, V2, and so on for the leaves. Okay, so you have here the complexity. So maybe it's easier to see this complexity bound that you see here. If I suppose that all ranks are bounded by big R, if the dimension of the spaces V1, V2, and so on are bounded by N, I will essentially have a complexity bound, which is like this. This part corresponds to the storage of the the internal core tensors. This corresponds to the storage of the top tensor, the tensor associated with the root, and these are the tensors associated with the leaves. The bound that you see here is linear in D, and it comes from the fact that for any dimension partition tree, its cardinal will be always bounded by 2D plus 1. Okay? The dimension 2D plus 1 for the number of nodes, a number of nodes equal to 2D plus 1 correspond to binary trees. So we will see later different examples of binary trees. But you can have also a very simple tree, which is trivial tree that I show you now. If I take this trivial tree, which is just with one level, I have just a first partitioning of the set of dimension into singletons. The representation of the resulting format in tensor diagram notation is the following one. You have one core tensor associated with the root and all these tensors associated with the leaves. And the format is known as the Tucker format. It is a very old format introduced in the, you see, not 2027, 1927. It has been used a lot. It is still used a lot in many applications where you don't have very high dimension, because you see that the tensor which is here, how many indices has? As many indices as the number of dimensions. So if you work in dimension D equal 100, maybe the ranks are not too high, but the complexity of storing this will be the rank to the power D. You see it. Okay? The leaves, it's okay, the storage of the leaves, but here you have a curse of dimensionality in this format, which is quite evident, because you have a core tensor of very high dimension. Okay, this is Tucker format, a particular case of tree-based format with a tree which is a trivial tree with one level. You have here also a very natural tree, which is a linear tree. So you split the dimensions into a singleton and the other variables. Again here, a singleton and the others, and so on. Okay. So each time you have a singleton when you partition a node of your tree. And the resulting format has been called tensor train Tucker format. You are more familiar probably, maybe some of you with the next formats that will come later, but okay. This tensor train Tucker format is a particular case of hierarchical tensor format. And this is a representation in tensor diagram notation. And this is a complexity, again, linear in D, quadratic in the ranks because of these internal tensors that you see here. And okay. And now come another format, the tensor train format that has been rediscovered by Ozoledets and Tertishnikov in 2009. It appeared much more earlier in quantum physics in the 60s under another name, matrix product state. And it corresponds to the tree-based tensor format I have introduced with a T which is not a complete tree. In fact, it's just a subset of a linear tree, which means that you will impose the rank 1 1, 2, 1, 2, 3, 1, 2, 3, 4, but I don't impose R2, R3, R4, and R5, okay? So it's a subset of a linear tree. The representation of this in tensor diagram notation will be like this. There will be no tensor now associated with this leaf, so you will have a train of tensors like this, okay? Each tensor having one leg, which is associated with a particular variable. And the explicit representation of this tensor, following the same strategy as before, and this recursive representation using representation of minimal subspaces and so on, it leads to this representation. Maybe you have already seen this format, tensor train format. So it's a multiple sum of evaluation of some functions, multiple sum of product of univariate functions. Okay. And the complexity of this representation will be now just quadratic in the rank and linear in the dimension. Okay, now I would like to give you another interpretation of this hierarchical tensor format as a class of functions that are compositions of functions. A tensor C alpha, which is this multidimensional array, can be identified with a multilinear function. Just like a matrix. You know this, if you have a matrix, it can be a matrix of size nm can be identified with a bilinear application that takes two vectors of size n and m and gives you U transpose AV, okay, for a matrix A and two vectors U and V. Okay. The same for tensors. If you have a tensor C alpha, which is an internal tensor in your tree, it can take as entries vectors of the size, the ranks of the children of your node, and give you as an output a vector of the size of the rank alpha. Okay? And this application will be linear in each of the entries. Okay? So you interpret this core tensor as a multilinear map. I call it here F alpha to change the notation. And what you can show is that the representation, an equivalent representation, is the following one, where you have multiple composition of functions. So here you have the feature map associated with x1 that gives you a certain vector of size R1. You apply to this a linear map F1 that gives you, the feature map gives you a vector of the size, the dimension of the space V1. The map F1 takes this vector as an entry and gives you a vector of size R1. The same for F2, same for F3, gives you here a vector of size R2, vector of size R3. And here you will have the core tensor 2, 3 that takes these two vectors and gives you as an output a vector of size R2, 3. And so on until the final multilinear map, which is here, which gives you a simple scalar as an output. And it's linear in each of the entries. So, okay, so you can call a tree tensor network a compositional function network where all functions that you composed are multilinear applications. Vector valued multilinear applications. Okay, so now if you will see another course this week introducing neural networks. You are probably familiar with these neural networks that are compositions of nonlinear functions, very specific ones. And in fact, it appeared quite recently that tree tensor networks is a particular family of neural networks that you can find in the literature. It has a name, not very used. They are not very used, not so used as other neural networks, as ReLU or RePu networks or networks with sigmoid function and so on. These are called sum product neural networks, where the activation functions in the networks just do multiplication and sums. Okay, you take entries of a neuron, the neuron just have an action of taking products of the entries and making summations. So if I take this tensor network here, this tree tensor network, with at the bottom here you see the feature map associated with the different variables. The graphical representation of the corresponding neural network is the following one, which is highly structured. Okay, so someone from neural networks, which is used to work with tensor networks, will see it's a sparse tensor network. This one has a sparse connectivity because I do not connect all the neurons of a layer with a neuron of the layer before. So it's a network with a sparse connectivity. The sparsity of the connectivity is associated with the dimension tree. And the number of neurons you have on a level is associated with the ranks, the alpha ranks that you have for the nodes of this level in the tree. Okay? So here I see 3 neurons here. It means that the rank R1, 2, 3, 4 is equal to 3. Okay? The rank 5, 6, 7, 8 is equal to 3. And so you have different ranks here in this tree, and so different number of neurons in these different sets. Okay, so this is a translation. So the depth of the tree will be related to the depth of the network. The width of the network, which is the number of neurons per layer, will be related to the sum of the ranks associated with this level in the tree. And that's it. And results in the tensor literature allow to say a few things about the properties of these neural networks. Okay, so some results on tensor networks have been used to say something about the properties of these things. Yeah.
Yes. So there is a question on the chat. They're asking what a sparse architecture actually means in this context.
It's sparse in the sense that, okay, if I had a fully connected layer, I would consider that all these red dots here are neurons associated with the first hidden layer. And a full neural network would consider also connections between these neurons and the output here of this feature map phi x3. Yeah, so here I have many connections that are killed here, okay, or the weights associated with these connections are set to 0 if you want. This is why you can call it a sparse neural network. Okay, I hope I answered the question.
When you defined the tree, you always said that you only up-bounded the rank. So does it mean that the number of neurons is in a way free up to some level? And if you do not bound some element, then you could put any number of neurons at that leaf or the corresponding node?
No, here it really okay. It depends on the architecture of the neural network. Here is determined by the tree, and the width of a particular layer is the sum of the ranks associated with your tree. So you control every width, all width of your neural network with this construction. Okay. An element of these tensor formats here with a given rank R is a neural network where you can say what are the bounds for the width of all the layers. Okay. Okay, so now I will not go into many theoretical aspects, but I give you an overview of the good things that we obtain with this format. Yes, there is a question there.
It's related to the previous question. So if you take the neural network representation, then you cannot like start from this type of neural network and then get a tensor representation of any member.
If you give me a sum product neural network with this sparsity, meaning that you don't consider at each level every possible connection that mixes all variables, but the connections are highly structured like this, associated with a tree, it is a tensor network.
Okay.
These sum product networks are tensor networks.
But even if we play with the rank and some ranks don't really correspond to some of the bounds that you mentioned earlier, and because we can still have the sparsity and have the issue of the rank and.
So there is another thing indeed. The thing is that I consider a set of tensors with a rank bounded by something given. It does not mean that the true rank of the tensor is, okay, there will be tensors in these sets having a lower bound.
Yeah.
Okay, a lower rank, sorry. Okay. Now, if you ask me the question, is there a tensor with a given rank? I give you R and I want a tensor with this rank. In fact, there are ranks for which there do not exist any tensor with these ranks. There are some compatibility conditions. If you remember, the conditions that have to be satisfied by the minimal subspaces, like R alpha is the rank alpha is below the product of the rank associated with any partition. So there are many constraints on these ranks. If you give me a tuple of integers that do not satisfy these constraints, it means that there is no tensor with these ranks. It answered your question, maybe?
Yeah, it answers my question. Yeah, thanks.
So, but the thing is that if you give me a sum product network like this, with arbitrary numbers here, it will be an object in this set with bounded alpha rank. The ranks will be bounded by the number of neurons you see here in each set, in each group. Okay, but the effective rank will maybe be lower. Okay, but not higher. Okay.
Sorry to follow up on the on previous question, but if it is higher, don't you have just a redundant representation?
Sorry?
If it is higher, if you don't respect these conditions and you have a rank at the higher level that is larger than the product of the ranks of the lower level, don't you just have a redundant non-unique representation?
It's redundant indeed. Yeah. It's just like represented a rank 1 matrix as a product of two rank 2 matrices. It's possible, but it means that you can compress.
Exactly. So you it still has a representation as a tensor, but it's just not non-unique.
Not unique representation. And even with matrices of rank, if you have a matrix of rank 2 that you write as a product of two matrices of rank 2 with 2 columns each, there is no unique representation also. Okay. So what are the properties of this set? So complexity of the representation is linear in D, polynomial in the rank, whatever the formats I have given, but okay. Other interesting property from a computational point of view is that this was for the storage, but it is true also for evaluation of the function. An evaluation of such a tensor for one value of the variables will be of linear complexity in D. If you want to differentiate your function with respect to x1 or with respect to x1 and x2 and so on, it will be also with linear complexity in the dimension. The same for integration and so on. So it has favorable properties from a computational point of view. Many operations can be performed with low complexity. It's not so nonlinear approximation tool because, as if you remember, it's just a sum of products of entries of tensors, or if you want, a combination of multilinear maps. It's not so nonlinear as could be a neural network with highly nonlinear activation functions. So this multilinear parametrization, in fact, you have a parametrization of a tensor as which is represented as a multilinear map with entries the different parameters. Okay, you remember this U of x, which is written as a sum of product of the C alpha, of entries of the C alpha. It means that U is linear in each of the parameters C alpha. And this is something, as you will see at the very end for the algorithmic aspect, something used in algorithms, okay? Exploiting this multilinearity. If you remember, the definition of the tree tensor networks is a set of tensors with all alpha ranks bounded for alpha in a finite collection of groups of variables. So in fact, it's an intersection of sets of tensors with alpha rank bounded. And if you remember, for order 2 tensors, the set of tensors with alpha rank bounded by some integer is a closed set. Since these formats are intersections of closed sets, it is a closed set. It's an a finite intersection of closed sets, so it's also a closed set. So it means that you have also well-posed of optimization problem in these sets. Okay. Also, we worked on we and many other people. I mean, you can find references at the end of this. You can also prove that these sets have a manifold structure, and you can exploit it to devise optimization algorithm exploiting these geometrical structures or dynamical low-rank approximation for evolution problem. And more importantly, I would say that there exist algorithms that are able to give approximation in these formats with controlled errors. I will come back on these algorithms later that are very important algorithms for maybe a reason why these formats are used a lot today is because there exist such algorithms where if you give me a tensor U, I cannot give you the best approximation in these formats for a given rank, but I can do it almost optimally. I can give you an approximation UR with the specified rank, whose error is bounded by a constant times the best approximation error in the set. Okay, it's the instance optimality Albert told about. You have algorithms that satisfy this instance optimality with a constant here, which is control. It will be of the order of square root of the dimension. So, of course, for very high dimensional problem, you may lose something with this square root if you have application, and there exist some applications in dimension 1,000, 10,000. It has been used in very, very high dimension, this object. So if you have, let's say, 100 dimension, you will have here a factor 10. So it means that maybe the best approximation error was 10 to the minus 4. You will provide something with an error certified at 10 to the minus 3. Okay? Not too bad. But you lose a little bit, but not too much. Just with constant in square root of D. Yes?
Square root of D is a pessimistic bound, or I mean, does it depend on the tree structure?
In fact, here I used the effective bound is the square root of the cardinal of T minus 1. But the cardinal of T is bounded by 2D plus 1, so here I simplified. Okay. It will be of the order of square root of D, but I can make it precise. It's square root of 2D, square root of 2D. So you have a square root of 2 here in front of D. Okay. And you can have even sharper result if you have a binary tree. You can remove a little bit to your constant. But essentially, it will be asymptotically in T. It will behave like a square root of 2D. Okay. Now, just a word. I will not tell you much about approximation properties of these objects, but here I introduce more general tensor networks. Before, it was 3 tensor networks associated with dimension partition tree. Here, it's another type of object for more general tensor networks that are defined, associated with graphs. So consider a graph here with here the solid shapes that are the nodes of the graph or vertices. And here are the edges of the graph. And you have also some free edges here, just lines emanating from a tensor, but not connected to another tensor. To this graph, I can associate a tensor network. Okay, where you have a tensor associated with each node of this graph. And each edge that you see here is a summation over the corresponding indices of the tensors that are here. So it works exactly as before. It is, the representation of this object is like this. It's a sum of product of entries of tensors. Some of the tensors depends just on summation indices, and some of the tensors depend also on the variable x1, x2, x3, and so on. If you give me a graph which is a tree, you end up with a tree tensor network. Okay, but this is a more general setting that you can find mostly today in the physics literature with many applications for the description of the state of complex systems that require these more general formats to be efficient. Okay, these are tensor networks that you can find in the literature. So, for example, the tensor ring here, it's, if you remember, a tensor train, but now you have a connection here between the first tensor and the last one. Okay? This is also called MPS, matrix product states with periodic boundary conditions. You have PEPs, MERAs, these are terminologies that you can find in the physics literature. Usually these tensor networks in physics are designed relatively to the geometry of your system. This be typically related to the representation of a state associated with a lattice of this, having this geometry. Well, so all these are not associated with tree, it's clear, because you have cycles in all of this tensor networks. And what about the properties of this tensor network? When a graph contains cycles, then it appears that the integers Re, which is associated with the summation indices at each of the edges, may not have an interpretation as the alpha ranks as before. Okay? So in the literature, you will see some people calling these integers here in the summation here, the bound in the summation as ranks, but it has no interpretation as a matrix rank as we have seen previously. Okay? In physics, it is called a bond dimension, which you can find also people calling this rank, but it's not exactly the rank. You call it as you want, but it's not a matrix rank. Yeah?
Yes, there is a question from the audience. What does MERA stand for?
Ooh, maybe you know, Mazen. There is entanglement for the E.
Multi-scale entanglement generalization Ansatz. So very simple, straightforward.
Yeah. Okay. No notion of singular value decomposition. What I told you before, I have algorithm not providing the best, but almost the best. I don't have it anymore here. I lose geometrical properties, no more a manifold, not even an algebraic variety. It's not closed set, so optimization problem may be ill-posed. Computational complexity increases. So if I want an exact evaluation of a tensor network represented like this, I will have an exponential complexity. But there have been a lot of work in this area with approximate algorithms. Many things are feasible, and these more general tensor networks are useful in many high-dimensional applications, in particular in physics and probably in other fields. Probably we will see these more general tensor networks coming in other application fields quite soon. What time is it? Okay. I have a few last slides on this first part. I would like to introduce them before the break. I introduce now a tensorization technique where you will see that all these tensor formats and tensor methods can be used for problems where you don't have multidimensionality. So I start with a very simple thing. Take a vector v in Rn, n equal to an integer b to the power L. Okay, so it's a vector with b to the power L entries. So clearly, this can be identified with a tensor by a reshaping, if you reshape this object as an array of size b times b times b times b, you end up with a tensor of order L. Okay, this is what you obtain clearly in Python with a reshape, and you will use it in the end-on session tomorrow. So I had a vector, I reshape it, I obtain a tensor. What is the correspondence between this tensor and the vector v here? That an entry I of the vector v is the entry I1, I2, I3 of the tensor v with integers here that goes from 0 to b minus 1, and that correspond to a binary representation of your integer I. This is one way to do it. There are alternative ways to represent an integer and map it to a tuple of integer, but this is a quite natural one. You introduce a binary representation in base b of your integer I, so that I denote like this, a tuple of integer between 0b minus 1. And you have then a direct correspondence between a vector and a tensor of order L. Okay? So the map which associate to a vector this tensor is a linear isometry between L2 spaces, the L2 space of vectors of size n, and the tensor space here equipped with a canonical norm. And what is the interest of this? In fact, there are many interesting operations in algebra that you can perform very efficiently in this world. Mapping a vector in this tensor setting, for example, you can compute an Hadamard transform, or equivalently a Fourier transform, or discrete Fourier, sorry, a discrete cosine transform, in a very efficient way, because the Hadamard transform applied to your vector v, okay, on the tensor v, bold v, it is the application of a very structured operator, a tensor product of small matrices, small Hadamard matrices of size 2 in general. The Hadamard transform is associated with the base b equal to 2. Okay, so these matrices are of size 2 by 2. The elementary tensor product of these operators is associated with the Hadamard transform for vectors of size 2 to the power L. So this reflects, in fact, the efficient complexity of this Hadamard transform, which will be in n log n. Quite easy to obtain from this the result that Hadamard transformation is can be done in n log n complexity. Okay, now, of course, you can repeat this also for tensors. You may have a tensor of size n by n by n by n, and each n is some b to the power L. So I have here initially a tensor with d indices, and for each of the indices going from 0 to b to the power L, I introduce a binary representation. Okay, so I can organize the different digits of this binary representation, or representation in base b, in different way with different orderings. So there will be multiple ways to transform a tensor into a higher order tensor, but okay, this is one particular way. And so I have transformed a tensor of order d as a tensor of order d times L. Okay, and doing this will allow to exploit some additional structure of these vectors that were not visible initially with the classical representation of your tensor. Here I transform it into a higher order tensor, and I could exploit structures associated with low rank of this new object V that I was not able to exploit by looking at this object directly. Okay, this was for vectors. Now I can do it also for functions. Suppose you have a function defined on an interval 0, 1. This is something we introduced with Mazen, and you will have a small exercise on this tomorrow. So what you can do is to split your interval 0, 1 into many intervals. Okay, you do a b-adic partition of your interval, meaning that the number of intervals here will be b to the power L. And each point x in your interval can be represented uniquely like this as b to the minus L, which is the size of an interval, times an integer I between 0 and b to the power L minus 1, plus a y, which is a variable between 0 and 1. The integer I just locate in which interval you are, and the y is a local variable that tells you where you are in the interval, okay? So it's a parameterization of the interval, a variable in 0, 1 with a few integers between 0 and b minus 1 and one variable 0, 1. Okay? And now for the integer, you do it as before. You represent it in base b. Okay, so I have a representation of this integer in base b with L digits. And at the very end, it means that a univariate function, a function of x, will be represented as a function of a local variable y and a set of L integers between 0 and b minus 1 that encode where, in which interval you are, the entry x is. Okay? So I have transformed a univariate function into a multivariate function or tensor of order L plus 1. Yes?
Yes, there is a question from the audience. So since the representation in base B coding here is not unique, does this choice of coding matter later?
Yes, it is unique, this representation here. I have an integer between 0 and b minus 1.
Yes, so I don't, so say 2 equal 1, 0, but 3 equal 0, 1. So I don't,
I mean,
for the
it depends what you call binary.
So
for a binary representation, for example, you have an example here.
They are specifying the questions.
The 0 is 0, 0. The 1 is no wrong. Maybe I can look at the question.
So no, it is more on the choice of the basis B.
Ah, okay. The impact of the B. So this is something yet unclear. This is I will show you some approximation results later, where we have many results where essentially the B does not have an influence, but it will have an influence in the constants. But now in practice, for a particular application, which B should you choose? It's not clear. There are applications where having b equal 4 is better than 5 or 3, and so on. So, okay, I don't have any clear answer on this. There is a flexibility here. If you work as a statistician and want to try a collection of models, I will encourage you to use first, to try to learn with the base b equal 2 and then 3, and then apply some model selection strategy to select the best. Because clearly there are applications where, and you could play with the libraries today if you are interested. Try to see the effect of this B, and you will see that it is not clear at all which B you should choose for a particular function. Okay. We can discuss this further tomorrow with those who are interested in playing with this tensorization technique. I could show you what to do with the library. Okay, some examples. So now we have a univariate function that we see as a multivariate function. So we could say, what is an elementary tensor in this world? An elementary tensor is a product of univariate functions. The first function is a function of the first digit I1. The second is a function of the digit I2, and so on and so on. And so this is an illustration in base 2. You have here an elementary tensor, which is just a function of I3. It is equal to 1 if I3 is equal to 0. and equal to 0 if I3 is equal to 1. And you have this step function, okay? This elementary tensor represents this step function where, okay, it is 1 on each of the interval where this digit of the binary representation of your integer is equal to 1. Here, a more complicated function where I multiply a function of I1, I3, and I7, since this is 1 only if I1 is equal to 1, the function is equal to 0 on this side, because any point x here will have a first digit I1 equal to 0. Okay? And here it's okay, 1 when I3 equals 0, and 1 if I7, so very high resolution. So you have many, step function with very, very small steps here. And here is a function where it depends also on the local variable linearly. You see here, function y times a function of I1, so you will have a piecewise linear function. Okay. And more generally, if you take for the function of y, which is here a polynomial, what you will obtain is a spline. Okay, highly structured spline, but it will be a piecewise polynomial. Okay, a few interesting observations. If you give me a polynomial defined on an interval, polynomial of degree p, if you write this q of x and you replace x by its representation with respect to I1, I2, and so on, so you have here a polynomial of a sum of the variable I1, I2, I3, and y. Okay? So you can write this multiple sum as a certain function of a group of indices, I alpha for alpha in 1L, and here a function of the complementary variable, including the y. If you write it like this, and if you decompose your polynomial q, you know that there will be a representation as a sum from 0 to p of these functions here to the power j times something depending on the other variables. What does it mean? It means that the alpha rank of the tensor associated with the function, with the polynomial q, is bounded by p plus 1, whatever alpha. So this was an observation done by Lars Grasedick a few years ago, and it has many, many consequences from the approximation results that I will tell you in the second part. So a polynomial function, if you have a polynomial function and you tensorize it, you see it as a multivariate function with this tensorization technique, the tensor associated with this polynomial will have all alpha ranks bounded by p plus 1. Okay? The ranks are controlled. The same for trigonometric polynomial. If you have you can easily show that this cosine of wx plus phi, whatever w plus phi, because x is the sum of the different variables, you expand the cos, and you can see easily that the ranks are all bounded by 2, and which means that if you have now a trigonometric polynomial, which is a sum of cosine and sine, a trigonometric polynomial of degree p will have a alpha rank bounded by 2p plus 1. So what does it mean? You will see the approximation results later. And this type of result will be used a lot for these approximation results, where we will use some approximation results that we know for polynomial approximation, approximation with trigonometric polynomial. And because we are able here to bound the complexity of the representation of these approximation tools using these low-rank formats, we will have a control of the error with respect to the complexity with these three tensor networks, or tensor networks in general. Okay? So these results on the ranks of the tensorization of these classical functions is very useful to understand the properties of approximation of this tensor network. Here's the same result on splines that we obtained with Mazen. that says that a spline which is defined over a b-adic over n b-adic intervals, I mean intervals that have been obtained by a b-adic partition of your interval, you can control the ranks also of these splines with respect to the number of intervals you have and the degree of the polynomials considered. And I finish here by, of course, the extension to multivariate function. This was for 1D function, but now if you have a function defined on the hypercube, each variable here in 0, 1 can be encoded as I did it before. Each of the variables will have its own binary representation with binary digits or b-adic digits and a local variable. And so you can see your function here as a multivariate function or tensor of many integers between 0 and b minus 1 and local variables. Okay? And a final remark is that the map which associate to a function its tensorization, we prove that it is a linear isometry between LP space defined on the hypercube to LP space defined on this product set here. So what is the consequence of this is that topological properties that you are able to show for tensor networks here will give you some properties of the corresponding function sets in LPs that you consider for approximation. Okay? So an interesting isometry property of this tensorization map. So you have here a few references, not much, but these are, let's say, surveys or books on tensors, introduction of what are tensors, what are the tensor formats, a reference in physics literature. After this, in the part for the second session, you will have much more references, much more specialized on particular topics. Okay? Other questions?
Yes. So there is a question from the audience. Is it possible to still efficiently compute matrix vector product using general tensor network formats?
The answer is no. If you have not exact, but you have approximate. If you have a, you mean an operator represented in with a tensor network format, and a general tensor network. You will have contractions to perform. Yeah, no. That's okay. That's okay. But okay, no. The problem will come when you will want to evaluate the entries of this final object. But if you have, let me say, no, I cannot start anything. Not for the other people. But if you have a tensor network, let me go back to the representation. Okay, if you have a tensor here with the entries, let's think about integers here, I1, I2, I3, I4. An operator acting on this object will have more indices. It will have indices associated with this one and additional ones. Think about the matrix vector product before. We have Aij and a vector Vj. The product of these things is just a new network with two tensors and one edge connecting these two tensors. If you have a tensor network representing an operator and a tensor network represented a vector, you will have the product, which will be a concatenation of these tensor networks. Yeah.
To answer the question, if you try to contract something like a PEPS format,
yeah.
So the one that had many loops in them, then indeed the exact contraction would be intractable. But
evaluation of the entries of the final object, but just formally writing what is the product.
Yes, sure.
It's just a graph with more edges and more lines. But evaluation, Essentially, it will be the same the same problems as evaluating the entries of such a tensor.
No, the question was really matrix product, computing a matrix vector product. So for me, that would be contraction. And to compute a contraction, this would be indeed intractable if you want to do it exactly. But you can do it approximately, heuristically, essentially eliminate cutting loops in between and still works fine.
The formal representation of the matrix product representation is a tensor network. But if you want to evaluate the entries of the resulting tensor, you have trouble.
Yes, there is one last question. So, is there a link between the tensorization map of a function that you introduced in the end and the so-called unfolding operator using periodic homogenization?
In periodic homogenization, I use this technique in a way that if you have a periodic structure, you can parameterize a point in your space with an integer telling you in which cell you are, which subset you are in this partition, periodic partition, and a local variable. So I would say, yeah, when you look at a function in periodic homogenization as a function of two variables, one indicating the cell, and one indicating the local variable, yes, it's a tensorization technique. It's a way to, in 1D, I would say it's exactly this. Yeah, X, it's B minus L, where B to the power L is the number of cells you have, I is the number of the number of the cell, and Y is the local variable. So yeah, I would say it's a natural representation in periodic homogenization, indeed. Yeah, we have to use it to exploit this tensor method in this world, seeing the function of X as a function of two variables and exploiting low rankness. For example, a periodic function will be a function which is a product. Will be a function just depending on the Y variable and not on the I variable. So a periodic function is a rank 1 function when you see it as a function of I and Y. Yeah. Okay.
So, yes.
Okay. Follow-up.
So should it? So a follow-up of the question on the value of B. Should it be related somehow to oscillation frequencies of the function?
Probably. In fact, I have the intuition that this B, playing with the B is like playing with local regularity of the function, but we were not able to quantify this thing. It's like, okay, you have two things in competition. When you will see the approximation tool, I will just, after the break, I will introduce you approximation tools based on this. I will use polynomial approximation locally, so I have to define a degree locally. But I have also this parameter B, how I partition the domain. And there is seems that there is a competition between these local degrees that you use and the B. They play quite the same role. That means that there will be related to some regularity of the function. The choice of these parameters is related to local regularity of the function you try to approximate, but I have no quantitative answer for the choice of B. I will tell you a little bit about the local polynomial degree, but not the choice of B.